Hey guys, so we're back at it. This is the first video for Wednesday, March 25th. Okay, so we're going to pick up with continuing to talk about what capital K is representing. Now, everything we've talked about to this point is what we would call homogeneous equilibria, which means everything's all in the same phase as one another. But there are times in which, and most equations we look at are actually heterogeneous equilibria, meaning that they're not all in the same phase. They're in multiple phases. And we need to talk about that because when it comes down to it, we don't include all four phases in our equilibria expressions. So there are four phases of matter that we write as far as not really four phases of matter, but there are four phases we include in balanced chemical equations, and those are solids, liquids, gases, and aqueous solutions, right? And you see everything on the slide right now except for liquids. So everything you see plus liquids. But here's the deal. So that's four things, but we're only going to include two of them in our equilibria. So what that means is the other two, while they may be present in the balanced chemical equation, do not get included in your K expression. So let's talk about why. Well, I mean, think about it. How would we express the concentration of a solid substance? We don't think of solids as being concentrations, right? We think of solids as being an amount. You would just put it on a balance and weigh it, right? Just like liquids, we only think of liquids as being volumes. You'd put it in a graduated cylinder and measure it. Now, if you're willing to sit here and manipulate the math enough, you could make liquids and solids look like concentrations, but in reality, liquids are volumes and solids are mass, and neither one of those on their own are a concentration. So what that means is we are not going to include solids and liquids in our heterogeneous equilibria expressions. And the reason for that is when we change their amount, it doesn't change their concentration. Water is water, whether you have 10 milliliters or a swimming pool full, right? It doesn't change the I mean, that doesn't even make sense, right? So let's take a look at an example here. So here we have the equilibria between carbon monoxide and carbon dioxide. And what we have here is we have some solid carbon as well. But the equilibria is between these two gas molecules. Yeah, you could double the amount of carbon, but think about it. You just changed the volume for both of the molecules. So their relationship to one another doesn't change, right? So yes, by adding more carbon, you diminish the volume in which these gas molecules can move around, but you did it for both of them equally. So you didn't affect the equilibria. So overarching statement, whenever you have a pure solid or a pure liquid in a heterogeneous equilibrium, we do not include them in the K expression, okay? So K is always concentration of products over concentration of reactants. So in this case, it would be the concentration of the lead ion raised to nothing, right? Because it doesn't have a coefficient, times the concentration of the chloride ion squared divided by nothing. And it's divided by nothing because the reactant is a solid, so we would not include it. Let's look at a couple of more examples. So here, my recommendation for you is the first thing I do personally when I look at these kind of questions is I mark through and identify anything that wouldn't be included. So right off the bat, I'm going to look and say, okay, a gas is fine, a gas is fine, a gas is fine. This is a liquid. Scribble through it. I'm trying to scribble through it with the mouse, but scribble through it, okay? So then K would be concentration of the products, but remember, we're not going to include this. So CO divided by the concentration of CO2 divided by the concentration of H2. Okay, we are not including water. Let's look at another example. In this case, you have four things present. So I'm going to do like a 5-second pause here, and then I'm going to tell you how many of these are actually going to be included. Yeah, so we're not going to include the two 10 things, right? So SN is 10. So Tin-4 oxide, not going to include. Why? Because it's a solid. The tin atom, not going to include. Why? Because it's a solid. So this is the concentration of CO2 squared divided by the concentration of CO squared. That's what the K expression is. Okay, we are not going to include the solids, and we didn't include the liquid. All right, so we've had a lot of practice with writing our K expressions, but everything we've done so far has just been writing a K expression. How do you actually start looking at this from a numerical perspective? Well, remember, K represents the relationship at equilibrium, right? At equilibrium. So if you know all of the concentrations of your reactants and products at equilibrium, then it's really straightforward. Step 1, write the equilibrium constant expression, and then step 2, you plug in all your numbers, right? And then you solve for what K is. Because remember, the only thing that changes K is temperature. So as long as they tell you it was done at a constant temperature, so another way to say constant temperature is iso, same thermal. So isothermal is constant temperature. As long as you know it's an isothermal reaction, then if you know all the equilibrium concentrations, then you should be able to get K from that. And remember, initial has nothing to do with what the K is going to be. So each one of these lines is a separate experiment, okay? So there's 4 separate experiments here. We had 4 different initial setups, right? Which led to 4 different equilibrium setups, right? But since they were all performed at the same temperature, K is exactly the same. And notice the values that are being plugged into K. They're these, right? The values being plugged into K are the equilibrium values, right? These are the equilibrium values. So who cares about initial? That's not what we're plugging into equilibrium. Okay, that's not what we're plugging into the equilibrium constant expression. So let's do, we've got a couple of examples that we need to do, but I'm assuming you would like to see me work these out on a piece of paper. So I'm going to end this video now, and then we're going to go to the next video in which I will work out a couple of examples for you. Okay? All right, I'll see you in the next video.